let us talk about the 6-low-PAN architecture. So the 6-low-PAN network contains three basic elements. One is sensor router, then edge router and the IP network. So sensor routers are responsible to acquire the data and route the measurement information to the edge router, which is connected with the IP network. And then these edge router will push data to IP network where all the other devices such as laptop or mobile phone or maybe servers and so on are connected. So in this way, the sensor router data travels to the server end or the software application end using IP network. Now, the 6-low-PAN network is the connected network where we can connect Ethernet, Wi-Fi as well as serial communication based networks together. Let's see how it happens. So in the field, we have various sensor routers which are utilizing the serial communication using the sensor devices, and then the data is pushed to the 6-low-PAN network using 6-low-PAN router as well as the 6-low-PAN sensor routers, and then using edge routers or 6-low-PAN routers the data is pushed to Ethernet, and since the Ethernet and Wi-Fi networks are interconnected, the data can ultimately be shared with Ethernet as well as the Wi-Fi network. So in that way, the field data which is acquired from the sensors can be immediately seen by the devices which are connected on the Ethernet or the Wi-Fi network. It is horizontally integrated, means the devices which are communicating over 6-low-PAN and the devices which are not communicating over 6-low-PAN but communicating over either Wi-Fi or Ethernet network all can share data to the applications at the same time. So that's why the devices, whether they are 6-low-PAN or not 6-low-PAN devices, can share data at the same time. Now let's see the 6-low-PAN network layers. So we use the standard TCP/IP protocol stacks for any software application or the any device which is connected over a standard TCP/IP network. So in the TCP/IP network, if you see, the TCP/IP network contains the Ethernet physical layer, then Ethernet MAC layer, IP layer, then the TCP or UDP layer, or we use ICMP also, which is Internet Control Message Protocol. And then on top of that, we have various applications such as HTTP or RTP kind of applications. So if you compare the TCP/IP stack with the standard OSI 7-layer architecture, you will see that the session, presentation and application layers have been merged together in the TCP/IP stack. So we have TCP/IP layer, and then on top of that we have the direct application layer. Now if you compare TCP/IP protocol stack with the 6-low-PAN protocol stack, you will see that Ethernet physical layer will be IEEE 802.15.4 physical layer in case of 6-low-PAN. TCP/IP Ethernet MAC will be now IEEE 802.15.4 MAC. Standard IP will be now IPv6 with low PAN capability, that is 6-low-PAN layer, which is integrated with the standard IP layer, and then the transport layer in both of the protocol stacks will remain same. The only change is that in case of 6-low-PAN we generally utilize UDP rather than TCP to save the response time. And then on top of that you have the same application layer in both of the protocol stacks. So application and transport layers are same in both of the protocol stacks. The only change is the lower three layers where standard IP is replaced with the IPv6 with the low PAN capability, and then the data link and the physical layers are based on 802.15.4. So if you see the structure of 6LoWPAN protocol stack, you will have 6LoWPAN interface layer which will connect the IP layer with the 802.15.4. The advantage of using 6LoWPAN network layers is that the devices which are on 6LoWPAN and which are not on 6LoWPAN can coexist. Means the standard TCP/IP based devices as well as 6LoWPAN devices can both work together in the same network because the other layers are same for both of the protocol stacks. So basically the 6LoWPAN is the interface layer which connects 802.15.4 frame to the IP frame. Now, the key factors for IP over 802.15.4, that is 6LoWPAN. So there are three major factors which we have to consider to make IP enabled 802.15.4 architecture. First one is header, where we are utilizing the standard IPv6 header. IPv6 header is of 40 bytes, while we know that entire 802.15.4 MTU, that is minimum transfer unit, is of 127 bytes. So if we use full IPv6 header, we will have very less space for data payload in the 802.15.4. So what we can do, we can utilize header compression technique so that the larger data payload can be utilized. Second is the fragmentation. Fragmentation is required because we have to ensure interoperability. That means the application data which flows from the transport to IP and then the data link layer will not be able to differentiate whether the data is going via 802.15.4 or non 802.15.4 layers. Now IP packets may be large when we compare it with 802.15.4 maximum size because IPv6 requires the link layer to support 1280 bytes of packet. So if you compare 1280 bytes is very large when you compare with the 802.15.4 MTU which is only 127 byte. So what we can do, we can fragment the data packets so that it can be fit into 802.15.4 maximum frame size. So this we will see how we can do it. And then the third important aspect is it allow link layer mesh routing under IP topology. So here 802.15.4 subnets may utilize multiple radio hops per IP hop, which is similar to what we see in case of LAN switching within the IP routing domain in Ethernet. So we might have one single IP router. Inside that we might have multiple subnets and multiple LANs where the data switching happens. So similar to that also we can configure the 802.15.4 subnets so that we can utilize the hopping capability. Now first we will see the 6LoWPAN header challenge. The network packet will have 40 bytes of the IP header and then in payload we will have the transport protocol data unit. So this total size of the network packet will be of minimum 1280 bytes which will be the part of the data payload of link frame. Now, if this packet is fitting into 802.15.4, which has the maximum limit of the frame size of 127 bytes, it is very difficult to fit 1280 bytes into 127 bytes without compression. So first option is that we will convert large IP address and header into a short address, and then we will make sure that the minimum transfer unit for 802.15.4 is ensured by fragmentation of the network packet, and then short range constraint is addressed by using multiple hops. So let's see how header compression happens. So in case of IP header optimization, the network packet header, which is of 40 bytes, is compressed and made up to 3 bytes. How we compress? We utilize the information which is already available in 802.15.4 header. The information which is there in IPv6 header, but it can be derived from 802.15.4 header, we can remove that information from the network packet header. What are those informations? The source address we can derive from link address. Destination address can also be derived from link address. Length information can also be derived from link frame length. And traffic class and flow level is not required, so we can remove it. So by doing so, we can reduce the 40 byte of header to 3 bytes of IPv6 adaptation header. Now, second important thing is the fragmentation. So here users are not limited by frame size due to IP interoperability over many links. So what we will do, we'll convert or we will fragment the large IP datagrams into multiple frames of 802.15.4. So all fragments of an IP packet will carry the same tag so that we can make sure that full data packet is again derived from the fragmented data packets. Each fragment will specify the tag size and position. The network packet data payload will be fragmented into multiple 802.15.4 link frames where you can link the various fragments so that you can stabilize the connectivity when you want to reconstruct the network packet. So in this case, the fragment do not have to arrive in order. They can come in any order, but at the network level, you will again reconstruct the network packet by adding them in a sequence. So the time limit for entire set of fragment is 60 seconds, means the all frames should be arrived and to be aligned within 60 seconds. So in that case, you will see that the time delay will be added because you will first fragment and then you again stitch them at the network packet level at the receiving end. So this will add the time delay. So that's why 6-low-PAN cannot be used for time critical applications. Now, third important component is the routing. So how we will utilize the routing? We already know that IP already has the multi-hop capability. That means routers connect the subnetworks to one another. The subnetworks may be of same or different physical links. Here, routers utilize the routing tables to determine which node represents the next hop towards the destination. Routing protocols stabilize and maintain proper routing table and exchange messages using basic communication capabilities. So IP routing over 6LoWPAN links does not require additional header information at 6LoWPAN layer because this can be done by utilizing the standard IP-based multi-hopping routing technique. What are the advantages of 6LoWPAN? 6LoWPAN turns IEEE 802.15.4 into next IP-enabled link. It provides open system based interoperability among low power devices over IEEE 802.15.4. That means IEEE 802.15.4 low power devices as well as full function devices on standard TCP/IP can coexist and they can exchange data with each other using the IP and the TCP or UDP layers available in the TCP/IP and 6LoWPAN network. It provides interoperability between low power devices and existing IP devices using standard routing techniques. It also paves the way for further standardization of communication functions among low power IEEE 802.15.4 devices. It offers to leverage huge IP based operation management and communication services and tools. Since we are using standard TCP and other layers by using 6LoWPAN, we can utilize the standard operation management and communication services which are available in various communication layers for IEEE 802.15.4 data also. It has a great ability to work within the resource constraint of low power, low memory and low bandwidth devices like wireless sensor network. Since 802.15.4 ensures the low power, low memory and low bandwidth, the devices which are on 802.15.4 can also communicate easily over standard IP network. Now when you compare 6LoWPAN and ZigBee, the ZigBee only defines the communication between 802.15.4 nodes and not rest of the standard network. It defines new upper layer all the way to the application which is similar to USB and Bluetooth rather than utilizing the existing standard. It also lacks in the transport layer. While in case of 6LoWPAN, it enables the communication between 802.15.4 to 802.15.4 devices as well as 802.15.4 to non-802.15.4 devices communication. It enables the use of broad body of existing standards as well as high-level protocol software and tools which are part of the standard TCP/IP stack. It focused on extension of the suite of IP technologies that enables the use of new class of devices in a familiar manner. So the biggest advantage is that by using 6LoWPAN, we can utilize all the standard functions which are part of the TCP/IP layers for 802.15.4 data communication also.